Thank you so much.
Good afternoon, ladies and gentlemen. Let's start with the final session on oxidation. We have a keynote lecture to start us off. It'll be given by Professor Graham Hutchings of Cardiff University. Graham was recently became a fellow of the Royal Society and obtained the Heinz Heinemann Award for the International Catalysis Society. His work on oxidation is very well known, as his work on gold and a lot of other systems. So Graham,
thank you.
The floor is yours.
Thank you. And it's a great pleasure to be here and give you a talk today on a topic that I don't often talk about, but I hope to talk a bit more about in the future, because I haven't spoken about alkane activation for a long time. It's one of these topics that you come into and you go out of and you come into again. And so at the moment I'm into alkane activation, but I notice it's a topic that a lot of people are quite interested in at the moment. So maybe something I say today will spark something in your minds. I was a little worried though when I got the invitation and saw that I was meant to be speaking in French. and anybody who knows my linguistic abilities, something I shouldn't have up to, but I've never passed a language exam in my life, ever, even at school, at elementary level. So to think that I could speak in French would be, well, it would be a very short talk. I'd chair, I wouldn't go over 40 minutes. So I was relieved to find out it was actually a French room. So, right, so the overview of the talk, what I want to put out is really, what I want to talk about is some work that we did with Dow and Lehigh University, Imperial College, and Cardiff University. These were the four constituents of part of the Diamethane Challenge, which was put in place in 2007, and we worked for a number of years on this. And so what I want to talk about are the sort of key results that have come out of that collaboration. And really this is the work that's come out of the Dow, Cardiff, Lehigh part of the project team. It's not the part that came out of the Imperial team. That's a different type of catalytic system, which is yet really to be published. So what I want to talk about is methane activation, an introduction to what approaches could be possible, what's been done in the past. Obviously you could give a whole lecture for days on what's been done in the past, so I'm going to scratch over that very quickly. So if I don't give you your favourite paper, I do apologise now. Everybody has their own favourite paper on methane activation, I'm sure. And so I do apologise now, and you can berate me later for not getting that copy. I'm then going to talk about gold palladium with hydroperoxide for methane activation. It would be sad for me not to say anything about gold. So you know I have a love affair with the element, and I was hoping that it would really work with this. We'll see. Then I'm going to talk about zeolite catalysts with hydrogen peroxide, and then come back to gold palladium with oxygen. So I think it's well recognised, and I don't really need to say it, but this is one of the key challenges, trying to make oxidized methane selectively to anything useful other than CO2 is a major target. And at the start of this, we would have accepted anything other than CO2 as the key thing. It's a challenge which really has been, and with catalytic chemists, probably the last 100 years. And probably every 10 years or so, there's a new impetus in the field. And I'll talk about some of those in a few minutes. But the key thing is, in the planet, methane, CO2 and water are all extremely abundant. And the reason for that is they're the thermodynamic sinks. That's where everything ends up. I could add carbon onto that as well, which is coal. This is where everything ends up in time. That's it. And so you've got to battle against thermodynamics. And so you've got to get kinetically to a product which is thermodynamically unstable. It really wants to go to CO2. So really, what really wants to happen is methane wants to go to CO2 when you react it with another abundant element, which is oxygen. So that's the problem with one's evidence. So the approaches that have become in the past, I mean, I started getting very interested in this field at much the same time as a number of other people, I suspect. And that's the selective oxidation at high temperatures, around 600 degrees, methane coupling, lovely paper by Lunsford and Ito in Nature in 1985, showing that MGO, and there was a paper before the break on MGO, so this is still a topic that is relevant at the present time. MGO for methane activation, it works, but it's all gas phase chemistry, which is not represented in that paper. And of course, before that, there's Madame Bassan's 1982 paper in journal Catalysis, Keller and Bassan, where they don't have the oxygen, and they take the oxygen from the lattice, and effectively they make methane as well. You put oxygen in the gas phase, everything goes in the plastic. But it's all radical chemistry in the gas phase, and that's the real problem. And there's a sort of 10% rule that one gets with that. Basically, you can get to around 10% conversion with 90% selectivity, in this case to ethene and ethane. It's very difficult to make oxygenates that way. I'm just skipping over this. There's a lot of work that's gone on showing with cool flames that you really can make methanol, and you can do some very interesting chemistry. When I move methane to methanol, sort of selectively, oxides have obviously come into the frame as being the catalyst that one would want to choose. And some work we did in the 1990s on gallium and molybdenum oxide mixtures sort of showed that if you had gallium by itself, this we thought of as activating the methane, and molybdenum oxide is activating the oxygen and activating, and the whole combination, not destroying the methanol that you were making. And we showed by putting this combination together, we could get a quite interesting catalyst. So it's brilliant, but we got an interesting catalyst out of it. We were a bit shocked when we realised that there's nothing new under the sun. It's a nice phrase that one should always bear in mind. Just because you've discovered something doesn't mean somebody else hasn't done it before you. And a very eminent UK chemist working in ICI used exactly the same approach to come up with a catalyst that would activate the methane and would activate the oxygen, in this case iron molybdenum, and got far better results than we got. And in fact, over oxide, this is around 26 moles of methanol per kilogram of catalyst per hour. And that really is quite a benchmark. And that predates all of the 1980s work. In the 1980s, there was thousands of papers on this. None of them will have beaten that. Then there's methane aromatization. In cycle, I started with propane and higher hydrocarbons. But if you have methane and you use molybdenum oxide instead of gallium oxide instead of sulfide, then you can make hydrocarbon, you can make benzene, toluene, xylene, but the byproduct of that is a lot of carbon, and that's what we want. So these are high temperature approaches, really, and so recent work is focused on getting the temperature down and thinking about biomimetic approaches to this. And of course, the obvious one to then look at is methane monoxide. This does it. This takes methane. It makes methanol. It does it very selectively. It has a di-iron active site, and this is encapsulated inside a pocket made up by these protein chains here. And it works by activating the oxygen, and it uses a very good hydrogenation agent, NADH, which donates hydrogen. I can't think of using this industrially. But the complete enzyme, using NADH as the hydrogen source, can make around 5 moles of methanol per kilogram of the enzyme per hour. And that's a rate of 5 minutes reaction time. So it's a sort of initial rate. But if you take basically the cofactor away, there's a cofactor which helps set up the hydroperoxide species. If you take that away, then the actual productivity, you can use hydrogen peroxide, but the enzyme itself, and now the productivity is a fraction of what it was, roughly 0.08 moles of hydrogen of methanol per kilogram of catalyst, or per kilogram of the native of the enzyme. And so those are the targets. When we started out this work, that's the target I gave the research group. I said, if you can't beat nature, then we actually haven't really done very much. Because nature's had quite a few million years to perfect this, and we only have 3. So maybe it's not a fair analysis. So what we also recognise, a lot of other people recognise, is that there's a copper form of MMO, and in fact a lot of people consider it's the copper form which is really the activity, it's the active form of this bacteria. But there's also a gold-containing enzyme which also works. Isn't that fun? Why is it nature managed to seek out a little bit of gold and make it work? Just goes to show there must be something in it. That's right. So, these are my pick of the previous literature for low temperature activation of methane. There's the Sheila Imperiana systems. These are the key references. Basically, these are using platinum salts in a very strong acid. The oxidant is a high oxidation state of palladium. It's made in situ. You make an ester of basically methyl sulfate. You use sulfuric acid, and you hydrolyze that to produce methanol. So that destroys the catalytic system. So you don't get one turnover. You get just a bit of it. And so if you could concentrate the acid back up and do that economically, that could work. But unfortunately, that last step doesn't work. So it's not a closed catalytic cycle. But it shows strong acidity, high oxidation state can work. And then there's the work of Sen and co-workers published in the 90s, where methane, again in a very strong acid, effectively what you're giving is a very good leaving group, which you then hydrolyze and you make methanol. And again, it is not a closed catalytic cycle. And then one paper, and very recently, something that we sort of picked out, there's this one in Advanced Synthetic Catalysis by Wang and co-workers, where they use a lot of homogeneous chloride, and amongst them is chloroauric acid. And they don't get much selectivity, but they certainly do get turnover of methane at quite mild conditions. So we thought that was quite interesting. So our approach that we started off at was that we wanted to use a liquid phase method for oxidation of methane. Of course, methane's a gas, but we wanted to use the liquid phase. We wanted to use a low temperature, totally much lower than people had tried before in this sense. So we wanted to be below 90. We didn't want to use any strong acidic media in the liquid phase, and we wanted water as a solvent very simply because it's got no carbon in it. Therefore, it can't confuse you. We can't make anything which is likely to be a carbon-containing product. That makes the analysis a lot easier. It makes the chemistry more difficult, but it makes the analysis easier. And this is a situation where you're going to be analysing for small amounts of material, so you want to make sure it's clean. So water, it turns out water is a very good solvent for this process. And we want to use a classic buzzword, environmentally benign, economically attractive oxidants, for example, hydroperoxide and oxygen. You'll see that that statement is not quite right at the end of the talk. And as Wang had shown that gold was a pretty good catalyst for this, but it precipitated during the process and could well have been a heterogeneous catalyst rather than a homogeneous catalyst in this process. And we'd already shown that gold palladium alloys were very active. We decided we would start with gold palladium alloys as I started. And just very quickly, our experimental protocol is high pressure autoclaves. I mean, more recently we've done this in flow reactors. I'm going to talk about that today. But we have stirred autoclaves and a set of what I call standard conditions where we can feed various gases into this. Typically 10 to the minus 5 moles of the metal present. We use hydrogen peroxide as the oxidant, 5,000 micromoles. We add that all at the start. This is not clever stuff because hydrogen peroxide decomposes. But we just want to do this simply. Methane is at 30 bar as a standard condition. And that means, of course, 30 bar up here, it's dissolving into the water. This is where the action's going on. We use 50 degrees as our standard temperature and around 30 minutes. And we stir it like crazy. So that's the analytical technique. We use liquid products we analyze by proton NMR with water suppression. We put a lot of effort into this, and you really can do it. We use 500 megahertz for most of the work, and these days lately we're using 600 megahertz. you can, with water suppression, it works very well. And using water as a solvent, you haven't got any interference from other materials in it. We also use GCMS and LCMS for validation of the products that we're making. And the gaseous ones, we use GC with a methanizer, FID, very sensitive to the amount of CO2. We put a lot of effort into CO2 calibration, because CO2 is in the gas phase, it's also in the liquid phase. You've got high pressure of CO2, imagine mineral water where you take the top off, it bubbles out of the water. So if you want to analyze the CO2, you've got to be able to sample the water as well as the gas, and that's crucial. So we do a lot of effort into that. And hydrogen peroxide is very simply done by filtration. So these are some simple initial results where we're looking at time online under our standard conditions. So this is up to 140 minutes here. But the most interesting thing is that the initial product that's formed is methyl hydroperoxide. And methanol and CO2 are formed subsequently. So methyl hydroperoxide is the primary product in this. And actually when you go back and look at a lot of other systems, methyl hydroperoxide is the primary product. You pick this up by NMR doing the analysis, because if you try and do the analysis by GC, you will decompose the methyl hydroperoxide into methanol formic acid. You won't see the formic acid, you'll see the methanol, and you'll think you've made a very selective system. So care on how one does the analysis. So methyl hydroperoxide is what you see first. And we looked at the effective temperature, we looked at a lot of reaction parameters. And the amount of hydrogen methanol that we're making here is minuscule. Okay? These are micromoles that are being made in our standard reaction mixture. And you can see that under these conditions, there is a lot more CO2, red is CO2, and green, I've been reliably informed by colorblind that is red, that is green. So the red is CO2, and the green is methanol. So the oxygen activity is around 20–25%, not very good, not what one's average at all. And as one goes up in temperature, you're not really changing that much, but you're making a bit more of the product. You're not really going up much from 90 to 70 to 90, and that's because virtually all the hydrogen peroxide is being decomposed before you start to do the reaction. So we thought, why don't we make the hydrogen peroxide in situ? We've got a catalyst system, we know there's the direct synthesis reaction with gold palladium. So let's just put the hydrogen and oxygen in with the methane. If you do that, then there's a slide. Oh, turned it off now.
Hit it again.
Hit what again?
The square.
Square. I'm glad you're there. I had to do that, otherwise he's got nothing to do. He's been lonely all day. Everybody's been doing this perfectly, and I come along. Right, I was trying to find out whether I'd missed a slide or not. Yeah, so I'd gone over this one too quickly. So now you can see this is doing it where we're adding the hydrogen and oxygen together, so in situ conditions. Now we're making a lot more methanol than CO2. So the in situ protocol, where you're making the hydrogen peroxide in situ and using it, is much, much more selective. And you can see this is now the time online profile, and initially one's making a lot of the methanol, but the real problem is that with time, the amount of CO2 that you're making, because now you're stirring this in the presence of making hydrogen peroxide with methanol that you've made initially, it's just being sequentially oxidized. And so you can get reasonable selectivities in short time. But really this was, and we did this some years ago now, I mean it's a pretty good demonstration that you can do this in situ. The problem is you can't make hydrogen peroxide fast enough to make the turnover of the next stage really work. So this in situ protocol doesn't really give you the amount of hydrogen peroxide you need to get the second reaction to go faster. And we were thinking about this, but the real problem we had is that the gold palladium systems were decomposing hydrogen peroxide a lot, and that wasn't good. Hydrogen peroxide is not cheap. And if it's a radical mechanism, then it would be a good idea if we could confine this system in some way, because then we might have a chance of trying to control the selectivity. And the last part is that acids stabilize hydrogen peroxide. And there's also been a key approach that's all been used in the really nice previous methanol studies. So why don't we just have a strong acid And obviously ZSM5 provides a nice strong acid and confinement. So let's use that. And so now in this slide here, this is gold palladium on titanium made by impregnation, and this is gold palladium on titanium made by deposition. And you can see that these are for the catalyst. This is the number of micromoles that we're making up here. Not very good. Blue is methanol, red is formic acid, and green here is CO2. But as soon as you put it onto ZSM5, it goes up dramatically. So ZSM5 supported catalysts. The group at this point think, we hit the jackpot. But luckily they did a key experiment, and that was the blank reaction, where you just put the ZSM5 in. What you find out is the gold palladium actually makes it worse over most conditions. So it's sad. Bubble is burst on gold palladium. I find a catalyst system which doesn't work for it. But so this is ZSM5 by itself. And so when you add these two together, it's a bit more of that. There is CO2 there, but it's not a huge amount. And there's a lot of hydrogen peroxide left at the end. So this isn't decomposing hydrogen peroxide. So of course at that point we switched everything. We went into the zeolitic systems, and the gold palladium stuff was totally put to one side. And we looked at other zeolites, anything we could get our hands on. And these is ferrite, beta, Y. ZSM5 stands out as being far more active than the others under the same reaction conditions. And if we looked at other materials such as silicolite and TS1, these have got the same MFI structure, so they can provide the same level of confinement, but they're not active. And so confinement is not the key point here. And so is it the aluminium, or aluminum, that's important, or is it the trace metal impurities? So if you look at the role of the silicon-aluminium ratio, then you can see that it peaks at around a silicon-aluminium ratio of 30, but there is no correlation really with the acidity of the aluminium content. And when we looked at this, we started to think about the previous work where ions ZSM5 have been used for N2O at high temperatures, with benzene to phenol, and also there's work with N2O forming alpha oxygen, which is then reacted with methane and you cool it down, and you can make a surface methoxide. So we started to think that maybe it's the metal impurities. We did a lot of work on this, and yes, it correlates, the activity correlates with the amount of iron that is in the catalyst. And then we did a lot of work on the structure of this material, and we were using the iron impurity from ZSM5. There's 160 ppm in the sample we were using. So that was the active component. And we with a lot of effort from EXAFS, joint work with Dow, computational modeling in Cardiff, we came up with this as a proposed active site for the whole reaction process. And of course, this is very similar to the structure that's previously been proposed for benzene and phenol, and it's very similar to the active site of NMR, in fact, it's almost indistinguishable. So there's no real surprise there. And we put a lot of effort into what we think is the reaction cycle for this. One takes effectively a mole of hydrogen peroxide to activate this center. You then go around this where you take another mole of hydrogen peroxide, you get the active oxidation species. You then react this with methane, and so you then need another mole of hydrogen peroxide to make the methyl hydroperoxide, which is the primary product, which then decomposes to form methyl on the separate catalytic site. So that is the primary product that's formed. And it requires 2 moles of hydrogen peroxide per mole of methane to go around it, and both the methane and the hydrogen peroxide are activated. So that is different from the MMO cycle, where only the oxygen is activated. In this case, the oxygen and the methane are activated by this heavy cycle. And when we do low conversion, and especially using flow experiments, we find that we can see the 2-to-1 ratio of the hydrogen peroxide to methane. And there's a lot of other things that are predicted by that mechanism. Yes, we effectively observe. So why, knowing that ZSM5 with the iron impurity works, let's put some more iron in there. And in fact, maybe we can put iron into other environments and it'll work even better. And so along the bottom here, you can see we've got silica, alumina, etc., etc. And these have all been added. We've added 2.5% iron onto these effectively by an impregnation process, by solid vapor. Come to me later. Age is catching up. Anyway, we put 2.5% iron onto them. You can see that ZSM5 stands out. And basically, if you put the iron in, we're increasing the activity by a factor of about 6. And the activity at 5 minutes is 35 moles of the oxygenated products per kilogram of catalyst per hour. So it beats the Dowden catalyst, which is good. It also beats the native enzyme system. So the group are very happy at this point. And then we thought, but the real problem with this is it's making a lot of acids. It's not making methanol. So in that slide there, where I'm saying this is products, these products that we're making are basically formic acid with a small amount of methanol. The over-oxidation. I shall now up the tempo. So this is the iron ZSM5, and you can see that this, the red, is formic acid. We also used copper ZSM5, and this was more selective to methanol, making a small amount of CO2. If you put the two together, now it just makes methanol. But ZSM5, unfortunately, decomposes quite a bit. This copper iron ZSM5 system decomposes a lot of the hydroperoxide, so it's still not the perfect system. But the interesting thing about the copper is you can add it as a homogeneous catalyst. So you can add a copper salt. This is without any copper present. And you can see there's only a small amount of methanol, a lot of formic acid, and this is the productivity. As you add copper, the productivity stays the same. This is copper in solution. But the formic acid goes down and the methanol goes up. You can do that by having a solid copper catalyst and a solid iron catalyst and just stir them together. You get exactly the same effect. And this is what one's doing here. This is iron silicalide 1, very active for making lots of formic acid. You add the copper, and now you're making essentially methanol. And so with these, you can get 10% conversion with 96% selectivity of oxygenates with no copper present. But when you add the copper, you get 93% selectivity with 10% conversion. So copper is a very important point, and what it does is it takes out the hydroxyl radicals which are responsible for the over-oxidation of methanol to formic acid and then onto CO2. So it very selectively takes out, stops the formation of those radicals. So quickly in the last bit, I've got 2 bits that we need to go through. One is, what about ethane? Ethane's easier to oxidize, yeah? Yeah, it is. But it's a lot more complicated. So we've got another carbon atom, but it's much, much more complicated. It makes a lot more products. Those of you sitting at the back, you probably need a telescope. But the primary products that one starts to see is acetaldehyde and ethanol. In fact, it's probably ethanol that goes very rapidly to acetaldehyde. There are a lot of products. But as you increase the conversion, this is time going along the bottom here, it's making acetic acid, which I'm sorry is very faint there, but that is acetic acid. So it's making a lot of acetic acid. This is ZSM5. If you add some iron to that, now the productivity goes up, and you're still making a lot of acetic acid. In fact, major selectivity is now to acetic acid in that system. So ethane oxidation to acetic acid using iron ZSM5. If you add copper, now the major product you're seeing is ethene. So copper changes the chemistry quite dramatically. So iron, you're making acetic acid, and at 70 degrees we can get 50% conversion, 70% selectivity to acetic acid. With iron copper, you're making mainly ethene, and we can get around 38% selectivity. We can choose conditions where we call our sort of high and low conversion, and we choose that by changing the amount of catalyst, say double the amount of catalyst, double the amount of hydrogen peroxide, double the reaction volume, and increase the amount of decrease, the amount of ethane that's in there, so the conversion will go up. And at high conversion, you can see that we're getting to around 50% conversion, and we're making a lot of acids in this process. So the selectivity of acids there is approaching 90%. So the chemistry that one's seeing with this is with methane, we're making effectively methyl hydroperoxide as the initial product, and that then goes to methanol. And methanol can go to CO2, it can also go to formic acid. And although this seems quite complicated, it's basically the only radicals we observe are oxygen-based radicals, either hydroxyl with copper atom and superoxide with copper present. With ethane, the situation is much, much more complicated. And now, by EPR, we see that we've got OH radicals present, but we've also got carbon-based radicals present. So with methane, there's no methyl radicals there. But with ethane, there are now carbon-based radicals present. And so that's the sort of summary of what I've been saying. The primary product is the C1 alkyl hydroperoxide. You can get a 10% conversion. With this one, though, it looks like there's 3 apparent primary products. You've got the alkyl hydroperoxide, the C2 one, ethanol, and ethene. We can get to 56% conversion. We can get, by tuning the iron or the copper, we can switch between acetic acid or ethene. Now, is ethyl hydroperoxide really a primary product? There's a lot of data on this slide. I'll go through it very, very well. We made ethyl hydroperoxide using basically an iron-on titanium catalyst, using a lot of ethane in D2O. So we have a stock solution of ethyl hydroperoxide. It also contains acid halide. So black is the ethyl hydroperoxide. We then put it in an NMR tube and look at how it decomposes with time in the NMR. So these are in situ experiments. And so you can see that it's decaying a little bit. Then put ZSM5 in, and you can see ethyl hydroperoxide, it goes very rapidly. Acetaldehyde is there, and now it forms acetic acid. With copper, ZSM5 forms acetic acid, and same with iron copper. It does not form ethanol. So when we look at this reaction mixture for the real reaction, very short reaction times, ethyl hydroperoxide is not present. It's not a primary. And so ethyl hydroperoxide does not decompose to ethanol. When you look in the literature, the organic chemists got there a long time before we did. So the last part of this is the further considerations. Because clearly we've got 10% conversion, 93% selectivity with methane, we've got high conversion, very good selectivities with acetic acid. Unfortunately, really you need to use oxygen. And why? Because hydrogen peroxide is more expensive than methanol. Now, it's a good job we didn't know that before we started, because I wouldn't have done all this work. It's been a lot of fun, okay? But let's put it this way, the group was a little bit unhappy when we found out they hadn't hit the jackpot. The next thing, the next problem is the temperature really ought to be above 140. Why? Well, any chemical engineer in the audience will tell you it's an exothermic reaction. You want to recover heat. Heat's a valuable commodity. So we were doing it at the wrong temperature with the wrong oxidant. Wow, it costs you. That's really bad. It does if you really want to work. So what we're going to do is we want to work this with oxygen, and then it can be a truly green process, mild conditions, etc., etc. How do we do this? Is it possible? Well, if it was, I probably wouldn't be allowed to be talking about it at the present time. And someone would be building a plant, hopefully. So we've given it a very good shot, I would say. And just to give you a little brief then, let's use toluene as a model for methane. It's not a very good model, but it's got 3 CH bonds on it. It's just we've replaced one of them with a very nice activating enzyme. So I know it's not a very good model, but it works. And so now we can go back to our gold palladium catalyst, and we can do solvent-free conditions. We can just put toluene in the reactor. This we can use at 120 to 160. And we can use oxygen as the oxidant. And when you do that, you very selectively make benzylbenzoate. And it's a very nice reaction. You can get, if you tune the conditions just right, you can get a 96% yield of benzobenzoate. Over a period, this is a long time, this is 110 hours. It's a very selective process, makes almost no benzoic acid and no CO2. And so we thought this was a very good model for methane. And the reaction pathway is why I think it could be useful. Okay? So here's the toluene. The first product we make is the alcohol. It then goes rapidly to the aldehyde. The aldehyde and the alcohol react to form the hemiacetal, and that gets oxidized to this. It does not go down this pathway to the acid at all. So it's very selective chemistry pushing in that way. Now, if you could take this big group away and just put a hydrogen there and do the same chemistry, you could end up with methyl formate. We spent 2 years trying to do this. And if anybody else wants to have a go, please have a go. We sort of run out of ideas most of the time. So it's a great idea that it doesn't work. Benzyl alcohol isn't a good model. Never mind. So my concluding comments. Nature uses enzymes to oxidize methane selectively to methanol with molecular oxygen. The rate isn't that good, but they know how to do it. They knew that you needed a cofactor and you needed to form a hydroperoxide species in situ, as I was talking about in situ formation of the hydroperoxide species, using NADH as the biological reducing agent. Very nice system. Zeolites with iron and copper, we can do this with hydrogen peroxide. As I already said, hydrogen peroxide is too expensive. So it's not the way. But you can tune these fine products by catalyst design. How much copper's in there, how much iron's in there. And there's probably lots of other things you can play with. And then finally, the gold palladium systems could be a way forward with oxygen activation. We know they work with oxygen. We know they work at the right temperature. It's just, can we get the right design to activate the CH1? At the moment, we haven't been able to do that. There's an awful lot of people who've contributed to this. There's a very large team in Cardiff. One of the key people was Kerry Hammond, who's in the audience today. At Lehigh, I haven't shown you any of the microscopy that Chris and his team did, but I think part of it. I think that the downlight would have been quite a struggle to see everything microscopy. Most people know he does extremely exquisite microscopy. And we ably helped by Eric Steinman and Henry Carter. In fact, they were sort of embedded in how we were thinking and how we were doing things. It was a great collaboration. So I'll leave you with a picture of Cardiff as it would look earlier today, because it's actually 9:40 at night. Well, actually, it's sort of setting sun at the moment. It's quite late, it sets quite late, so this could be the dark blue sky. And the CCI is in this building here. It's a lovely building, lovely historic building. I keep asking the Vice Chancellor and my boss for a new building, because we really would like to get a new building. If he knew what we were getting up to with hydrogen and oxygen, he would want to see a new building as well, because that's his office. We might just be able to get it. And with that, thank you very much.
We have time for a few questions.
The mechanism of your chlorine oxidation.
Yeah. Oh, I'll go faster. That one, yeah.
Could you stop anywhere as an intermediate and just stop?
Yeah, well, we know if you just take the benzyl alcohol, then you can oxidize that very selectively to benzaldehyde. You can get a 92% yield in a 10-hour reaction using exactly the same catalyst at 100 degrees. So that we knew we could do, and it doesn't go to benzoic acid. Okay? But when you do this, because this first step is far trickier, as soon as you've made this, it goes very rapidly. So if this is K1, that's K2. K2 is many more orders of magnitude higher than K1. So you can't trap that out. Not easy.
One more question. No questions?
I've shocked them into silence.
One, the ZSM5, you showed a lot of the zeolites were not working. Only that one seemed to work.
Yeah.
And you showed a mechanism involving the protonic site there.
Yeah.
Really, is it the acid, or is it really the structure?
No, it's the structure. Basically, the aluminium allows you to absorb, or basically absorb the iron, so that you can create the right structure. So aluminium is acting as an anchor, but the shape of it is crucial to get the whole thing. So yeah, it's nice to together.
Well, thank you very much.
Thank you very much.